तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In one-dimensional problems, there is an interesting theorem which essentially says that the ground state has no node, the first excited state has one node, the second excited state has two nodes, and so on. So the question is, why does the number of nodes increase as the energy increases? And a very crude answer is the following, although one can make this very formal. It is called the ordering theorem. It is because on the x axis you would like to have a wave function that is normalizable, that means it must go to 0 at both ends. So it starts off with 0 and then it must end at 0 on this side. In between, whenever it goes up, it has to come down. Okay. So if it goes up and comes down a repeated number of times, you can see the curvature keeps changing up and down. So the second derivative term contributes significantly. And the larger the number of nodes, the more the contribution, and therefore the larger the energy on the right hand side. So in a very rough sense, you would expect that the ground state of the system would be something where these gradient terms do not contribute at all, something which goes up and has to come down. So the simplest way for it to do it is this fashion. Therefore there are no nodes at all. Every time there is a node, it means there is a maximum, then there is a minimum, and then the curvature terms contribute more and more. So that is a rough idea of why, as you increase the energy, as the energy eigenvalue increases, the number of nodes in the wave function also increases. Okay. Now we can prove some fairly general theorems on what the wave functions look like in a one-dimensional potential problem. I will make some statements and later on we will see how to make this with more experience. We will see how to substantiate this. If you have a potential of this kind, a V of x, which is perhaps something which goes to 0 at the ends maybe, and then it goes up, it comes down, there is a well, and then it does this, and then maybe it comes down in this fashion. In such a potential well, one could ask, what do the energy eigenvalues look like? What do the Hamiltonian's eigenvalues look like? First of all, if it is a bound state, it must be normalizable. This means the wave function must vanish at the end sufficiently fast. Okay. Now clearly you could not have an energy level below the least value that the potential takes, and that is not very hard to establish, because after all the equation that you write down looks like p squared over 2m operator plus v of x operator acting on phi of x, or the state vector is E phi of x. Where in the x basis v of x operator is just multiplication by v of x, and this stands for the second derivative if you like. Now that is the eigenvalue equation that you have to solve. In a general sense, this term here, the kinetic energy term, in general please remember the kinetic energy does not commute with the potential energy, because x and p do not commute with each other. Therefore this particle cannot have a definite value of its kinetic energy simultaneously or in the same state as the one in which it has a definite value of its potential energy. In general, the eigenstates of the Hamiltonian are not eigenstates of the kinetic energy or the potential energy separately. That is crucial to remember. That is completely different from classical physics, where you can actually take the total energy and say so much is kinetic energy and so much is potential energy. Although the Hamiltonian is the sum of the potential and kinetic energy terms, please remember, in a stationary state of the system, the particle does not have a definite value of either its kinetic energy or its potential energy. but only of the sum of the two. That is simply because x and p do not commute with each other. Okay. However, we can say that no matter what state you are in, this contribution can't be negative, that is for sure, even in the quantum mechanical case. Why is that? Because in any state psi, an arbitrary state psi, I take p squared psi in any normalized state, this is the expectation value of p squared, and divide by 2m and you get the expectation value of the kinetic energy. But this is equal to the norm of the state that you obtain by doing this, because remember that p is a Hermitian operator, therefore you can write this p squared as p dagger p, and it is just the scalar product of this eigenvector of this state vector with its adjoint, and therefore it is the square of the norm of that state vector. And you know the square of the norm of a state vector cannot be negative, it is 0 only if and only if the state vector is the null vector in the vector space. So this proves that the expectation value of the kinetic energy is always positive, okay. And then it is a trivial matter to prove that you cannot have an energy of this kind, because this would imply that the expectation value of the kinetic energy is negative, the expectation value is negative. The other classical idea you must get rid of is to ask, when the particle is here, what is its energy? Such a statement has no meaning at all, because the position operator does not commute with the Hamiltonian, and therefore the question of the particle having a definite energy when it is in a particular place does not exist, does not occur at all. The particle is actually local everywhere, there is a probability amplitude for the particle to be anywhere on the x axis, and all you can ask is what is the probability if the particle, when it is in a certain state, an energy eigenstate, it lies between this point and this point, that is it. That is the sort of question you can answer. But you must get out of this classical way of thinking which says that with the particle you can associate a path, a trajectory, so that at every point in every instant of time you can associate both a position and a momentum with it, nor should you think that the particle, when it is in an eigenstate of the total Hamiltonian, has so much kinetic energy and so much potential energy. That is not true either, nor should you think that the particle has so much energy when it is at this point or when it has this momentum. Those ideas are classical and they are completely invalid in quantum mechanics, okay. Once you appreciate that, then it becomes much easier to understand. So my point was that because the expectation value of the kinetic energy cannot be negative in any state of the system, simply because the kinetic energy is a Hermitian operator, the square of a Hermitian operator, it is of the form p dagger p if you like, and its expectation value cannot be negative. It implies that there can be no energy levels lying below the least value of the potential, okay. You could have an energy level here at this value, but the wave function of the particle in general would not be confined to this region, it would in general be an extended wave function. There is a probability to find it outside in this side, a finite probability, but that is a completely non-classical region. Classically, of course, if you tell me this is the total energy of the particle, you would simply say, look, it oscillates back and forth in this potential well between these amplitudes, between these turning points. That is no longer true quantum mechanically. The wave function, if I plot, would corresponding to this energy value would be something localized like this, in this fashion, dies off sufficiently rapidly, and definitely with overwhelming probability it would be inside this well. But there is a finite non-zero probability for it to be outside the well, as outside its classical amplitude as well. Could you have an energy level of this kind somewhere here? Let us say the potential goes to 0 infinity. Could you have an energy value here, or could you have an energy value here? Could you have some eigenstate like this? The answer is not strictly. These cannot be strict stationary states, bound states, because what would happen if you had an energy value here is that there is a barrier, a potential barrier classical potential barrier in this region of finite width and finite height, and there is a probability for the particle to tunnel through from here to there. If you start with an initial state here and wait long enough, you would have a non-zero probability of finding the particle there. So there cannot be a strict bound state once you have escape possible by tunneling. Exactly similarly, you could not have a particle localized at this point. If you start by putting the classical quantum particle in this at this point or in a small range about this point initially, as time goes along this state would evolve under this Hamiltonian such that you end up with a finite probability of finding it in this well. So it has tunneled through this well and it would tunnel through here, and then of course it can reach all the way up to infinity, which means the wave function cannot be normalized anymore, okay, and ditto on this side. However, it is possible, for instance, if I find an energy value here, if I start with the particle here, if this barrier is long enough and high enough, and similarly here, then the tunneling probability could be exceedingly low, and you might find the particle inside this well for a very long time, but eventually it is bound to escape, and such a state is called a metastable state. So you have metastable states here, but then eventually things would tunnel through, okay. Tunneling is something we may not have time to get to, but it is a quantum phenomenon, completely quantum phenomenon. Had this barrier been infinite in height with a finite width, then there is no possibility of doing this, because then really has to overcome an infinite barrier. So the tunneling probability depends on the range, how much of the what is the width of the barrier, as well as what is the height of the barrier, okay, and it decreases exponentially in the height of the barrier. So if the height goes to infinity, the tunneling probability goes to 0, okay. Suppose you had a delta function barrier, could it tunnel through? Yes indeed, yes indeed, because now even though the height goes to infinity, the width goes to 0 and there is a tunneling probability across. But if the height is finite, the width is finite and the height is infinite, then it is not possible for it to tunnel. Similarly, if the width is infinite, of course if this thing goes on, if this potential goes like that and asymptotes to that value on that side and the same value on this side, then an energy level here is definitely possible. There is nothing for it to tunnel through, it is an infinitely wide barrier on this side. So those are the sort of rough guidelines which you must use, but I emphasize once again, you have to get over the classical idea that the particle has a definite energy when it is at a definite position. That is not possible, okay. It is a completely classical idea, it is not possible, okay. Now let us do one more property of these wave functions, and after that let us solve the harmonic oscillator problem. And the property I had in mind was, what happens if the potential has a certain symmetry? How is it reflected in the eigenstates or the eigenfunctions of the energy? So let us look at a situation where you have a potential, and I will not specify it at the moment, V of x, which has some shape like this, it is a symmetric shape, say x squared or x4 or a combination of x squared and x4 or something like that, which is completely symmetric shape. Now what kind of states would this is supposed to be symmetric, I have not drawn it too well, but it is okay. What you are given is V of x equal to V of minus x, you are given this, that is a symmetric function about the origin. Now what kind of eigenstates or energy eigenvalues would you expect? By what I have said earlier, you could not possibly have any energy eigenvalue there, no negative values here below the least value of the potential, which I will without loss of generality take to be at the origin, okay. So if I take this as a 0 level of energy, you can't have negative energy levels in this problem. Could you have positive energy values? Yes indeed. You could have all sorts of energy levels here, and in general, because the particle is confined, you would end up with a discrete spectrum. Suppose this potential well had been of this form, had asymptoted to some level what kind of eigenstates would you have, what kind of eigenvalues would you have? You would have a discrete spectrum here certainly, but then you could also have a continuous spectrum up there. Beyond that it is not bound anymore, and the particle could have non-normalizable wave functions which would correspond to a free particle zipping from the left to the right, but as it zips across, for instance if you shoot a particle from the left, as it zips across it is really as if it is entering a medium of different refractive index, because out here you could say the potential is essentially 0 or a constant, and therefore it is like a free particle, but once it comes here there is a certain potential, and therefore the effective k squared changes, and which means that the wave number changes, which means that the particle propagates as if it is going through a different medium to the other side. But let us look at simple cases such as this, only bound states, so it goes off to infinity on this side and infinity on this side. One is guaranteed that all the eigenfunctions of this in this potential, all the eigenfunctions of the Hamiltonian are in fact normalizable, they all correspond to bound states, and you have a pure discrete spectrum. Now I add the condition that I have V of x is V of minus x. What is it that one can say? Well, please remember that each eigenfunction must obey this. d2 phi x2 plus V of x phi of x equal to E phi of x. And now let me make a change of variables, let me make a transformation of variables from x to x prime. So let x prime equal to minus x, a change from x to x prime. So it proceeds in 2 steps, one has to be careful in this argument. So I change variables, I can shift variables, I can always do that. What happens to this equation? It becomes minus h squared h cross squared over 2m d2 phi of minus x prime, because x is minus x prime, over dx prime 2, because this does not change sign, it is a second derivative and therefore does not change sign, plus V of minus x prime phi of minus x prime is E phi of minus x prime. I have merely rewritten the same Schrodinger equation for the eigenfunction phi of x and the eigenvalue of E in different coordinates. Okay. But V of minus x prime is V of x prime by symmetry, right. So here I can replace this by V of x prime. And I can drop the prime, I could call it anything, call it x or whatever, or y, call it anything you like. So what does this tell you? It is exactly the same Schrodinger equation as before. So it says if phi of x is a solution of this wave of this equation with eigenvalue corresponding to eigenvalue E, so is phi of minus x, right. What does that imply? If the system is not degenerate, what does that imply? There is no degeneracy in one dimension, therefore every eigenfunction, every eigenvalue must have a unique eigenfunction. But now I just proved that if phi of x is an eigenfunction with eigenvalue E, so is phi of minus x. Therefore it implies that phi of minus x must be linearly dependent on phi of x. It can't be anything else, it must be linearly dependent. So this implies phi of minus x equal to some constant times phi of x. Okay. There is no other alternative. That immediately implies that c squared is 1, because I can now go from minus x back to x once again, and therefore c is plus or minus 1. So this immediately implies this is only possible if and what does plus imply? What sort of function is phi of x? Even function, and the minus sign is odd functions. So this proves that if the potential has symmetry, reflection symmetry, the potential has parity symmetry invariance, then the solutions have definite parity. So I am saying that if the potential is an even function, the wave function, I am not saying the wave function must necessarily also be even, I am saying the wave function must be even or odd, but it can't be a mixed function. So if the Hamiltonian commutes with the parity operator, HP is 0, that is the statement that we have just made, the Hamiltonian commutes with the parity operator. This implies that the eigenfunctions of the Hamiltonian are also eigenfunctions of the parity operator. Every eigenfunction of the Hamiltonian is either an even function or an odd function, and therefore they can be classified into even and odd functions. What would the ground state be? We can make a statement about the ground state immediately. Would that be even or odd? It would be even, because the wave function has to be continuous, and if it is continuous and an odd function, then at x equal to 0 it must be 0, which means it has a node, but the ground state does not have nodes. So the only possibility is that the ground state is an even function. So you would in general have an eigenstate like that, an eigenvalue like that, corresponding to an eigenfunction like this. This would be the ground state. So if I call this level E naught, this would be phi naught of x. In general there would be some level E1 here, and that would be an odd function, one node, it would do this. And then a level E2 does not have to be equally spaced, some level E2, and it would be an even function. It would perhaps do something like this, 2 nodes, but an even function. So under fairly general considerations, simply by using the symmetry of the potential, one can come to a conclusion that the eigenfunctions would be ordered even, odd, and so on. Now here is an instance where two operators commute with each other, and we are finding a complete set of common eigenstates of the two, but all functions, all even functions are not eigenfunctions of the Hamiltonian, of course not, these are very specific Hamiltonian, but all eigenfunctions of the Hamiltonian are eigenfunctions of the parity operator simultaneously. The class of eigenfunctions of this operator is much greater than the class of eigenfunctions of this. A subset of this are eigenfunctions here. So having seen this, let us see whether we can actually substantiate this by doing by solving the Schrodinger equation in the simplest case. The simplest even potential, which is smooth and so on, which you can think of, is x squared. We put that in, and that is the harmonic oscillator. But even before I do that, let us look around this in one more direction and ask, what do I expect? What kind of eigenfunctions or eigenvalues do I expect? It is important to try to guess the answer. So we have this classical problem, this problem of a Hamiltonian, which is p squared over 2m plus a v of x, and this v of x I am going to take to be some even function, just a power of x, an even power of x, say. So let me take this some lambda, which is a constant, x to the power r, and let me just to make it more general, let us take this to be an even function, any power r. So let me make this modulus here. Okay. Of course you immediately see that at the origin there will be a point when it would have a cusp if r is equal to 1 for instance, but that is not serious, the potential is okay, allowed to have it. What does the potential look like for r equal to 1? For r equal to 1, what does it look like? It would just be a thing like this. R equal to 2, it would be a parabola. R equal to 3, it would be steeper. Remember that I am allowing for singularities here, so it would be even flatter going up like this. R equal to 4 and so on, it goes up. How about r equal to half? What does it do? Well, I mean it will still do something like this, right? R equal to half, this is r equal to 1, 2, 3 and so on. In all these potentials you would expect a set of bound states, discrete levels, all of them. Okay. What does the particle do classically? What would it do classically? What would be the phase trajectories? What would they look like? Well, the phase trajectories of this particle, if I plot x versus p, this is classical. They will be closed curves, there will not be ellipses unless r equal to 2, there will be some closed curves. So you have some kind of amplitude for a given energy, and then the particle would execute some crazy thing like this. If r is equal to 2, it would be an ellipse, but if r is equal to 4 for instance, then it would be a sort of very flat oval of this kind. R equal to 1, yeah, it will be all kinds of curves, it could even be this, we do not care, we really do not care. What we would like to do is to find out semi classically what is integral p dx equal to. So when the particle is executing these trajectories, what is integral p dx, and then I apply Bohr quantization. Integral p dx is the area of this curve, it is just the area of this curve and inside the curve, inside the loop. And how do we estimate it as a function of the energy? So classically what you would say is, for a given set of initial conditions you would find the Hamiltonian h of xp, you would say this is equal to E, and this is given to you, some positive number is given to you as the total energy of the system, and then it swings back and forth exchanging kinetic and potential energy, and we want to know what the area under the curve is. Now it is clear that at these points the potential energy is 0 by construction and the energy is completely kinetic classically, and what is the intercept here equal to? Square root of 2me, because all the energy is in the kinetic energy. So this intercept goes like e to the power half, apart from the root 2m and all that. And what does this intercept go like? Well, the energy is completely potential at this point, no kinetic energy, so it is clear that this goes away and you get x to the power r is E. Therefore this amplitude goes like e to the power 1 over r. Therefore what does the area go like? Just the product of the two, right? I mean, apart from numerical factors, this area whatever it is bigger than this triangle and it is smaller than the rectangle, and the area of the triangle is half base times height. So as far as the energy dependences goes, this thing here is proportional to e to the power half plus 1 over r. you are guaranteed that that is true, apart from 4 pi's and things like that, numerical factors. But this we are advised is n times Planck's constant. When you do Bohr quantization, it says these orbits are quantized in a funny way such that integral p dx is n times Planck's constant. This says that En, the energy level to the power 2r r plus 2 goes like n, or En is proportional to n to the power 2r over r plus 2. So it says simply that at sufficiently large values of the quantum number n, when you expect the argument, the classic semi-classical argument to be valid, the energy levels En must change with the quantum number n according to that law. We are not saying what is going to happen in the ground state or the first excited state, that requires detailed calculation, but for sufficiently large n this is going to be true. Is this clear? Okay. What happens if you set r equal to 2? It becomes proportional to n. So I expect that in the simple harmonic oscillator problem, the energy levels, I do not know what is going to happen near the ground state, but sufficiently far away, when n is much bigger than 1, I expect the energy levels are going to be proportional to n itself, n to the first power. What happens when r is equal to 1? 2/3. So it says it is sublinear, less than, does not increase as fast as n, less than n to the first power. The energy levels do go up all the way to infinity, but increases sublinearly. This means if I took a ball, a potential which is constant, x mod x is essentially a constant a linear potential, that is like mgh, the potential. So if you for example bounced a quantum ball up and down on the ground, then the potential, of course it hits the ground and it cannot go below that, but this is linear, mgx if this is x, and then the particle would bounce back and forth classically, but quantum mechanically the energy levels in this potential here are guaranteed to increase like n to the power 2/3, n to the power 2/3, less than proportional to n. What happens when n is when r is equal to 4, quartic potential? Yeah, it increases faster than n. What is the maximum it could increase? It can only go up to 2, because as you increase the power, this potential gets flatter and flatter. So here is x, here is v of x, and you end up with potentials which look like this, very high power, and then as r tends to infinity, it goes like n squared. That is the worst it can do. And what does the particle in a box do? Goes like n squared. Now you see why the particle in a box went like n squared. It was really like taking and putting it in a potential and then making the potential infinitely high. The slope becomes infinite, and then it ended up with n squared. It can't do anything more than that. Now you could say, well, I have taken problems in which the power was x to the power r, and I kept on increasing r such that finally it reached a vertical slow lines, I mean rigid, like a rigid box. But more than a power, you could have an exponential. What would happen if the potential goes like e to the power x? We would like it to be symmetric, so let us make it e to the power mod x or cos x. So what would happen to this problem? What would be the energy levels like? So here is x, and let us make it cos x minus 1 by adding a constant, so that the energy levels really look like this, the potential looks like this. This is the cos function. it's symmetric, cuts the axis at 1, so I got rid of that by putting the -1 there, and then it goes exponentially fast. So this guy here is like e to the power x, and this guy here is like e to the minus x, because e to the minus x is negligible here and e to the plus x is negligible here. So it goes like this, exponentially fast, faster than any power. What would the energy levels look like? They can't go faster than n squared, they can't increase with n faster than n squared, because that is already for an infinitely high wall, rigid wall. But at the same time it can't be a power less than 2, because then that would mean a finite r. So what would happen? So let me write this out. En must increase slower than n squared as n increases, for arbitrarily small right, it can't go like n to the power 2 minus, it can't go like 1.999, that is not allowed, nor can it go like n squared, must be slower than. What would it do? Huh? N squared by log, where did the log come from? Do you believe that? I mean, n squared by log what? It's faster. You believe that? You put out this log from somewhere. How can it be? It can't be a power less than 2. It can't be 2. What would it do? He is suggesting n squared divided by log. Log what? Log n. N squared over log n. Does that sound reasonable to you? Yes? Why not log n? Why not log n whole squared? Does the idea of a logarithm sound absurd to you? No? How many people think that's absolutely stupid? Everybody is polite. What do you think? Very good intuition. That's exactly what it does. There's a logarithmic correction. That's the one that's weaker than the power, and let's see what it does, how to do this. You see, once again, a very simple calculation, once again in x and p, these are some kind of ovals of some kind, but this amplitude here is e to the half, because that is the kinetic energy, and look at what the potential energy would do. What would this be? You see, if you say this is equal to E, the energy E, and P is 0 on this axis, then it says cos x is like E, right, but cos x is dominated by e to the x for large values on this side. So e to the x is like E, or x is like log E. So this is like log E. Now the area inside the curve is e to the power half log E, that is the product of this times that, and this is n, and you got to solve this equation. That is not easy to solve, because it is a transcendental equation, there is both power and a log. It is not easy to solve, but you solve it by iteration to leading order. This does not vary very much. So to leading order, it is clear that E goes like n squared, so you put that in here and then do an iteration. So, or better still, take logs on both sides, so you get half log E plus log E is like log n. This is much smaller than this guy, so it immediately says log E to first approximation is like 2 log n, or E is like n squared. Substitute that in this, so it says e to the half log n squared is like n. but log n squared is just 2 log n, we do not need that thing there. So e to the half is like n over log n, or en is like n squared over log n squared. So the guess was almost right, it is just log n whole squared. So although you can't solve this problem, it is a very difficult differential equation to solve with this cosh, you can't solve it explicitly, you still can estimate what is going to happen to the energy levels for very large values of n. There is a logarithmic correction to the power law. Okay. Now let us get back to our simple harmonic oscillator. We have enough machinery now to ask, is this solvable exactly or not. We would like to explicitly solve it. There are many ways of doing this, it is the most fundamental problem in quantum mechanics at this level for very deep reasons, and it appears over and over again all the time because of this single property which I will explain right now, which we will see explicitly. The energy levels are going to be equally spaced, as you all know, and this is the reason why it makes an appearance once again in quantum field theory, because in a nutshell, when you take many particles, you include relativity, you include the possibility of interactions, you do all kinds of crazy things and you put all these particles together, then when you want to describe a free gas, a set of free particles which do not non-mutually interacting particles, or a free field, what is called a free field, and you want to quantize it, every time you add one more quantum of the field, you are adding the rest energy of this particle, of this quantum. Therefore addition of one more particle is addition of a constant amount of energy to the total energy, and then you would like, therefore it is natural that what appears in this problem is precisely the harmonic oscillator solution in disguised form, because this has exactly discrete energy levels which are equally spaced. I have to say right away that the harmonic oscillator is not the only potential which has equally spaced level. There is an infinite family of potentials called isospectral oscillators, all of which have equally spaced levels, but this is the first member of the lot and the simplest of them. Okay. So now we are in business, let us try to solve this problem. Our task is to solve the linear harmonic oscillator. The Hamiltonian operator, let me forgo these for a moment, p squared over 2m plus 1/2 m omega squared x squared. And just as classically you are given the fact that x and p obey a Poisson bracket relation, quantum mechanically you have the fact that x commutator p equal to IH cross times the unit operator. The first thing you got to realize is that in the position basis p is a differential operator minus IH cross d over dx, but that is only in the position basis. The energy eigenvalues would be independent of what basis you choose to describe the problem. That is just one way of describing the state vector, the position basis. So it is like choosing a particular coordinate system to describe an abstract vector, but the eigenvalues and the state vectors corresponding to these eigenvalues are independent of what basis you choose to solve the problem in. You could solve it in any basis and transform to whatever basis you like, and this is what Dirac did. He found an operator method of solving these equations. Now of course the operator suggests immediately there is an algebra, matrices appear somewhere and so on, but I would like to disabuse you immediately of the notion that you can do this with finite dimensional matrices, because this commutation relation precludes the possibility of being able to represent this system in terms of a finite dimensional space. The Hilbert space is infinite dimensional. You cannot express these operators as finite dimensional matrices, and that is immediately true, because the moment you write xp minus px equal to IH cross times the unit operator or the unit matrix, if you write it as a matrix representation, and take trace on both sides, we know that trace AB equal to trace BA even if A and B do not commute, as long as A and B are finite dimensional matrices. So the left hand side would give you 0, this is equal to that, so the trace and if it is finite dimensional, the trace of the unit operator is just the dimensionality of the space, that is finite, and this is 0. So this is a contradiction. It is not possible to write X and P in terms of finite dimensional matrices. Okay. So this identity is no longer true, and you can't make such a representation. We will see that you need infinite dimensional matrices if you choose to use a matrix representation, but if you use the differential operator representation, then there is no question of matrices anyway. Okay, alright. So we would like to solve for the eigenvalues and eigenfunctions. One possibility is to say, if there is an eigenvalue E and the eigenfunction is phi of x, then this must be equal to minus h cross squared over 2m d2 over dx2 phi of x plus 1/2 m omega squared x squared phi of x is equal to E phi of x. And one tries to solve this, we know from the shape of the potential already that E must be some non-negative number. So we already know that E is a real number and a non-negative number because the potential has a minimum, absolute minimum at x equal to 0. And then the question is, does this equation have solutions? You need to put boundary conditions, and what are the boundary conditions? You would like it to be bound state, you would like it to be normalizable. So the natural boundary conditions would be to put boundary conditions phi of x goes to 0 as x tends to plus or minus infinity. Both sides it must vanish. After that we would like to normalize this wave function. It is some number, if you find it to be 6 for instance, then you redefine your phi as 1 over square root of 6 times the original phi, in which case you have normalized it to unity. So this is the strategy. What sort of differential equation is this? It is an ordinary second order differential equation, but there is a slight complication here. This coefficient is not a constant, it is a function of x, which means that you can't solve it simply as a superposition of two exponentials. That original trial method of trying exponentials does not work because the coefficients are not constants. What is the solutions to this equation called? This is an example of what is called Hermite's equation. Not quite directly Hermite's equation, but it can be transformed into that, and then the solution appears as the product of an exponential factor e to the minus x squared multiplied by some constant times a polynomial in x, and these are called the Hermite polynomials. So you need to use a more sophisticated method to solve this equation. You need to use this method of series, the Frobenius method. Are you familiar with this Frobenius method? So you need to use that to solve this equation here. But what we will do is to follow Dirac and solve this equation by a much cheaper method, an operator method, which gives us the solution explicitly without going through this difficult, relatively difficult boundary value problem. Although it is simple enough as it is just a little messier to do this. The hard part is that it is a second order equation. Had this been a first order equation, you could write down the solution by a very simple formula. So Dirac's trick actually reduces to saying that this becomes a first order equation. And let me even say this so that you appreciate what is going on. This is a second order differential operator, right? So it is minus h cross squared over d over 2m d2 over dx2 plus half m omega squared x squared acting on the wave function. And what Dirac did was to break this up into two factors, two first order factors. Once you do that, then a solution of this equation implies that each of these two factors, if they commute with each other, acting on the wave function must give you E times phi. So it just factors this second order differential operator into two first order factors, and then the answer is more or less obvious immediately. Another way of saying it is, I have x squared plus p squared If I want to write it as a product of two operators, of two factors, what should I do? How do I factorize x squared plus p squared? X plus or minus ip. So that is exactly what Dirac did. So let us see how he went about it. The first step is to reduce these, is to get rid of this messy IH cross factor. This thing, I want to get rid of this I times H cross. I would like to make it simpler. So define an operator. By the way, there is a length scale in the problem. The parameters in this problem are m, omega and H cross. Those are the parameters in the problem, right. So out of these parameters you can construct a quantity of dimensions length and dimension of x and dimensions p. And what is the quantity of dimensions length? The length that you can construct, this length is equal to H cross has m L squared t to the power minus 1, right, and m t inverse is m omega. So so I could construct H cross by m omega square root is a length. And what is the momentum? How do you find a momentum? Momentum is mass times velocity, it is mlt inverse. So if I took m omega H cross, this is m t inverse and then m L squared t inverse, and I took the square root of that, I get mlt inverse. So this suggests that square root of m H cross m omega, that has dimensions of momentum. So when I construct new operators which are linear combinations of x and p, I may as well get rid of these dimensional quantities. So let us define an operator A equal to x divided by this guy here. So it is dimensionless. Plus IP divided by H cross. And A dagger, this is not Hermitian, these are Hermitian, but this operator is not Hermitian because I have got an I sitting there, and that operator is x over square root of H cross over m omega minus IP over square root of H cross. Okay. So I am writing x plus IP and x minus IP, but when I multiply the two I get x squared plus p squared, and I have got this factor half sitting here. I would like to get rid of that too, so let us make this a 2 here, root 2. This will make the Hamiltonian look very simple, okay, because I got rid of that. When I multiply the 2 I get 1 over 2 root 2 1 over root 2, that gives me a half, and that will exactly match this. The first thing I got to ask is, are these Hermitian operators A and A dagger? Definitely not, they are not Hermitian. So these directly are not physical observables, these they are combinations of these operators here, and there is this important I factor out there. What is this equal to? What is A with A dagger equal to? X commutes with itself, P commutes with itself, so I got to take the commutator of this with that and add it to the commutator of that with this here. This with that, you can see what is going to happen, it is a half sitting in the denominator because of these two things here, and then there is an H cross, so there is an H cross in the denominator. This m omega factor cancels because it is in the denominator here and in the numerator there, and then x with p is equal to I H cross, and the I with minus I gives you a plus 1 and an H cross, but the H cross cancels with whatever was in the denominator, but the half remains. And then in the other term, this with that is exactly the same thing, except now you get a minus sign, you get a minus I, but there is a plus I here, so that again gives you a half. So it is immediately obvious that this is equal to 1, exactly 1. It has been normalized in such a way that it is exactly 1. And remember, A and A dagger themselves have no dimensionless, physical dimensions are m to the 0, L to the 0, T to the 0. So it is a great advantage to be able to write the Hamiltonian in these dimensionless variables. And what happens to the Hamiltonian itself? This becomes equal to, now we can see all we have done is to factor this Hamiltonian with that h cross and omega put in. So this is equal to h cross omega A dagger A plus a half. I leave you to verify that you get this extra term there. Okay. This is the well known oscillator Hamiltonian written in terms of A and A dagger. By the way, these operators have names. This is the first example of what are called ladder operators or raising and lowering operators for a reason which will become clear. Okay. They are also called creation and annihilation operators in quantum field theory. They really are, this is the starting point of quantum mechanics in some sense. Okay. So our job now is to find the eigenvalues of this operator. This is half times the unit operator incidentally, so I should write that down. It is understood. We have to find the eigenvalues of this operator given this commutation relation. A with A, this should be the unit operator incidentally, but I am just going to write it as A dagger equal to 1. It is understood that it is the unit operator. Incidentally, that again shows that it cannot be finite dimensional, because trace A dagger is trace A dagger A, but that is not equal to, that is 0 and can't be the trace of the unit operator for any finite unit operator. Okay. Now Dirac's solution was the following, and this is due to Dirac. This method is due to Dirac. P.A. M. Dirac was one of the founders of quantum mechanics, as you know, and he is the one who proved the equivalence of the Schrodinger and Heisenberg pictures. He gave the operator formalism of quantum mechanics. Okay. That was in fact his PhD thesis, and possibly the only person in the world who could ever have a PhD thesis whose title was quantum mechanics. Just that, quantum mechanics. Okay. A few years later, when he got was very young when he did this. A few years later, when he got the Nobel Prize and he walked into the high table at Cambridge in his college, there was a round of applause, and then Lord Rutherford, who was presiding over the table and who had already got the Nobel Prize, and there were several other people who had got it already. When the applause went on for a little longer than Rutherford thought it proper, he sort of growled. He said, "That is enough of that. This is not the first time the prize is coming around this way." So there was Dirac was a great one of the greatest physicists of all time, and his idea was to introduce these operators, which has now become very standard fare in quantum mechanics. He is the one who first understood the idea of he introduced the Bra-and-Ket notation to start with. He also called it transformation theory, because the whole thing was just going from one basis to another and how to write things in different bases and so on, and he essentially laid the foundations of the modern way of looking at the subject. Okay. Now what is the problem? Define n equal to A dagger A. I use a symbol for this thing, and the reason will become clear in a minute. I will call this operator capital N. It is called the number operator for a reason which will become clear. The reason is that n's eigenvalues will turn out to be 0, 1, 2, 3 and so on. They will be the natural numbers. Now what is the commutator of n with A? And you see the power of the algebraic method. It is completely algebra, nothing more than that. By our rule for commutators, which follows from the rule for Poisson brackets, we know that A with BC is A with B, with C on the right hand side. Never change the order of the operators. B appears on the left, C appears on the right. So the commutator of A with BC is A with B with C appearing outside, and then B on the left, A with C in this fashion, and similarly AB with C is similarly, exactly similarly, A with C with B on the right hand side plus A on the left, B with C. Okay. These are fundamental rules for commutation for commutators, and all we have to do is to apply that here. A commutes with itself, so this part is 0 and all you have is A dagger with A with the A on the right hand side. This A goes out and is on the right hand side, but A dagger with A is minus A with A dagger, so this is equal to minus A. And similarly N with A dagger is very simple, it is A dagger A with A dagger, and that is equal to A dagger on the left hand side, A with A dagger, that is equal to A dagger. Okay. So there is a little algebra that is formed here. The original algebra was A with A is 1 0, A dagger with A dagger is 0, A with the unit operator is 0, A dagger with the unit operator is 0, and A with A dagger is 1, the unit operator. That formed an algebra called the Heisenberg algebra, and once you add n to it, once again you can see there is a kind of closed algebra. The commutator of any of two of these guys is linear combinations of the same set of operators. Now suppose our job is to find eigenstates of this guy. This is trivial because this is a unit operator, anything is an eigenstate. This is the operator whose eigenstates we have to find. So let us suppose there exists an eigenstate. Let lambda be an eigenvalue, and let us suppose n lambda. I should really write psi with a subscript lambda to show it is an eigenstate with eigenvalue lambda, but let us abbreviate notation and just put lambda inside the ket. This is the operator, this is the eigenstate, this is the eigenvalue, this is the eigenstate. What do we know about lambda? What do we know about lambda? Can it be any arbitrary complex number? It must be real, because A dagger A is Hermitian. You take the Hermitian conjugate of A dagger A, you get A dagger A once again. So after all, it is the Hamiltonian apart from a constant, so this guy here must be real, guaranteed to be real. That is all we know for the moment. Then take that statement n with A equal to A, this guy here, and apply it to an eigenstate, this eigenstate. So I have this operator identity and I apply each side of this identity to the same state, eigenstate lambda. This implies n A lambda minus A n lambda equal to A minus so it says n acting on A acting on lambda, this is already a ket vector, some ket vector, and n acts on it. What is n on lambda? By definition that is lambda on lambda, right? It is a number, this guy is a number. So I move it to the right hand side and I get lambda plus 1 A on lambda. What conclusion do you draw from this? It says lambda minus 1. What conclusion do you draw from this? Yes, if this is an eigenstate of n, then so is this operator acting on lambda also an eigenstate of the same operator n, but with an eigenvalue reduced by unity. In exactly the same way, you take n with a dagger on lambda equal to a dagger on lambda, and use the fact that it is plus a dagger there, and it tells you that n acting on a dagger acting on lambda is equal to lambda plus 1 a dagger. So it says if lambda is an eigenstate, if ket lambda is an eigenstate of n, then so is a dagger acting on ket lambda with an eigenvalue increased by 1. So a dagger is called the raising operator and a is called the lowering operator, because it lowers or raises, these respectively raise and lower the eigenvalues of n. So it is not surprising that this guy is called the raising operator, and this fellow is called the lowering. Together, of course, you could call them ladder operators, they go up and down. Okay. But we still do not know what lambda is. So if I start with some lambda, I apply a on it, I get another eigenstate with eigenvalue lambda minus 1, I apply a once again, I get another eigenvalue with a minus 2, lambda minus 2, and so on. This will keep going down below. Eventually, since lambda is real, it will hit a negative value. But you cannot have a negative eigenvalue for a dagger a. Why is that? N cannot have negative eigenvalues, because in any state whatsoever this operator a dagger a psi, that is the expectation value. Forget about eigenstate, any arbitrary state, this is the expectation value of this operator, and this is equal to the norm of a psi whole squared, exactly as I did for the kinetic energy. It says take this ket vector, take its bra vector, and take the inner product, that is the square of the norm. If the expectation value can't be negative, it means all the eigenvalues, which after all the expectation value is an arithmetic average over eigenvalues, that can't be negative either. No eigenvalue can be negative, because in no state of the system can this have a negative expectation value. So what does that tell you? What is the only possibility? Lambda is a real number, you start with some lambda, it is a real number, but then if lambda is an eigenvalue, lambda minus 1 is, minus 2 is, lambda minus 3 is, until it hits a negative value. It is not allowed to hit negative values. Lambda must be an integer, you must have started with an integer. So you have no choice but to say that lambda must have been some integer, any positive integer, and then you can keep going down till you hit 0, but you can keep going up all the way to infinity. So that at once proves that lambda must be equal to n. And n is 0, 1, 2, that is it. The least values it can have is 0, it can't be negative, that is it. Pardon me?
Why can't it be all of them shifted by some?
Suppose it is 1.1, then there is an eigenvalue 0.1, then there is an eigenvalue 0.1 minus 1, that is not allowed. Right?
Why don't you say the same thing here?
Pardon?
0 minus 1 is also.
No, there exists a state such that A acting on it must give you 0, and then what do you do next? It is now 0, finished, the eigenvalue has become 0. There is no way you can lower it after that. So it implies there exists a state 0 such that A acting on 0 is 0. and then to go to -1 you would have to act with A on that, but it is already gone, it is 0. So it can't be a fraction. If it were 1.5 then it would go to 0.5 then go -0.5, no, there must be a state with eigenvalue 0 such that A acting on that eigenstate is 0, it annihilates this state here. I should really call it phi subscript 0, but I use this notation lambda. This state is the ground state. In field theory it is called the vacuum, and the annihilation operator A annihilates the vacuum. When it acts on it, it gives you the null vector, that is it. 0 is not the null vector in the linear vector space. This vector is not the null vector. This is 0 times whatever vector you like, it does not matter, it is the null vector. This vector here stands for phi subscript 0, just my notation that I use this 0 here. Our job is to find out what are these states, what do they look like, and so on. So what I do is the following. The next job is to find the eigenstates n, because we now know that A dagger A acting on n is n on n, and incidentally the Hamiltonian acting on n is h cross omega n plus half unit operator acting on n is h cross omega into n plus half. So these are the energy levels. There is that extra half, it is called 0 point energy, and it says the lowest energy level in this harmonic oscillator is not 0 but half h due to quantum fluctuations. We will see the significance of that. So it essentially says that in a potential like this, classically the equilibrium state is when the particle is sitting here at rest. 0 kinetic energy, 0 potential energy. Quantum mechanically this is not possible, because if you localize the particle at the origin, its uncertainty in momentum becomes infinite. So you can't have a state of absolute rest, does not exist. The ground state energy is here at this point at half h cross omega, and the next first excited state is h cross omega with 3 halves h cross omega over 2, and then 5 halves h cross omega, and so on. Equispaced energy levels all the way to infinity. Now our job is to find the eigenstates n, and then to explicitly represent these eigenstates I need to find the wave functions. I have to go back and phi n of x for each of these guys. But you see, suppose you start by saying, start with the 0 normalized. So let us start by saying I have the ground state and I will normalize it. I will find its explicit representation later on, but let us say it is a normalized eigenstate. Okay. Then I would like to find the first excited state. What is this equal to? It is A dagger acting on this guy, right? That is what raises it up by 1. This corresponds to eigenvalue 1 of the number operator n, but I am not sure if it is normalized or not. I need to normalize this, so I put some constant here, some constant times this guy. In general, if I start with this eigenstate n and I apply a dagger on it, it is going to go to n plus 1. So let us write it in general. Let us write n plus 1 is equal to some constant which may depend on n, a dagger on n. In general that is what is going to happen. I raise with the a dagger, I lower with the a, and I want this to be a normalized state. So the question is, what is this Cn equal to? Now how would I do this? Take the bra vector on this side, so n plus 1, n plus 1. If that is 1 by construction, all these eigenstates are normalized, then this implies that mod Cn whole squared n a dagger on n is 1, because I take this guy and I take its bra, and the bra of it is n bra and then an a on this side. But what is this equal to? Can I simplify this? Can I simplify this guy? I don't know a, I don't know what a dagger does on n. I know what a does on n, but I don't. What should I do? What should I do? I use the commutation relation which says a dagger minus a dagger a equal to 1. I use the commutation relation. So it says a dagger equal to n plus 1, because a dagger a is the number operator, and therefore this is n plus 1 on n. But this is an eigenstate of the number operator with eigenvalue n, therefore this is equal to mod Cn squared n plus 1. Okay. And if I insist that should be equal to 1, then it immediately tells you that Cn apart from a phase factor is 1 over square root n plus 1. That guarantees that all my eigenstates of the number operator are normalized. I start by saying I have a set of normalized eigenstates, and now I am asking how do you go from one eigenstate to another? By applying a dagger you move upwards, but there is a constant factor multiplying it. So it gives me the first piece of information. That is how it raises, preserving normalization. In exactly the same way, n minus 1 is found by applying n a on this guy here, and there is some coefficient d sub n which I would like to find out. Then if these states are normalized, n minus 1 is 1, this is mod dn squared, and now I take this guy here and this is just a dagger a, and here it is very simple, I do not even have to apply the commutation relation, and this is equal to dn squared. This is just the number operator n on n which gives you the number n and then a normalized state, so so it gives you the other piece of information that this dn is root n. This is why when it hits 0 it stops. So a on 0 is 0 because of this, and there is no state minus 1, so it is completely consistent with that. So these are the pieces of information you need, that is it, is automatically 0. Now let us see what the wave function looks like. We put in all the x's and p's and things like that and see what happens. To avoid doing a second derivative, solving a second order differential equation, I simply choose this equation. A on 0 is 0, choose this. But what is A? In terms of x and p, what is this? This is x divided by root 2h cross over m omega plus ip over root 2m omega h cross. That operator acting on 0 is 0. Can we get rid of some of these constants? This is root m omega by 2 h cross, so x root m omega over 2h cross, and this 2h cross we can get rid of. So let us just write m omega x. I would like to find out what the ground state wave function is, phi 0 of x is. And what is phi 0 of x, by the way? By definition this is x 0, by definition that is the representative in the position basis of the ground state vector 0. That is the definition of the ground state wave function in the position basis. So let us do this on both sides. What is this represented by? Minus IH d by dx acting on x on 0, right. So this says minus I plus I cancel, so you get h cross d over dx phi 0 of x, that is this on that, plus m omega x phi 0 of x must be 0, because this operator acting on this ket vector just gives you x, they label x. This is the equation that must be satisfied by the ground state wave function, right, and it is a first order differential equation, it is a trivial equation to solve. So what does it tell you? It says phi 0 of x equal to some constant, let me call it a0, normalization constant, we will put that in, times this is m omega over h cross, this goes away. So you got d phi over dx plus constant times x phi equal to 0. What sort of solution? E to the power minus the integral of this guy, and that is x squared over 2. So it immediately says a0 e to the power minus m omega x squared over 2 h cross squared. That is the solution. What kind of function is that? It is a Gaussian, no nodes, so it starts off like this bell shaped curve, that is guaranteed to be the ground state wave function of this problem. And we did this painlessly, no second order equations need to be solved or anything like that, painlessly. What is a0, how do we find it? All we have to do is to normalize it. So phi 0 of x norm squared dx minus infinity to infinity equal to a0 squared, I will choose the phase to be 0, so this is just a0 squared, then the square of this integrated minus infinity to infinity, that is a Gaussian, and you know the integral of a Gaussian e to the minus ax squared is square root of pi over a. So this is equal to square root of pi over a in this case is m omega and then at 2 h cross squared. Right. So it says a0 and I want this to be equal to 1, this is A0 equal to m omega over 2 pi h cross squared to the power 1/4. So I put that in here and I get m omega over 2 pi h cross squared to the power 1/4 times this. That's my ground state wave function. Nice Gaussian. How do I find the first excited state? Cheaply, without solving a differential equation. It's
also m omega squared by
h cross. Pardon me?
the exponential.
Is it h cross squared or h cross? I don't know. I didn't keep track. If you say so.
We can check that.
Yeah, it's h cross. Yeah. Okay. So how do you find the first excited state? I apply a dagger on what? I use this relation. I use this relation here. So how should I use it? I'd like to find state 1. This state is equal to 1 over square root of 1 a dagger on state 0. The x representative of it is this, and that is equal to phi 1 of x. Therefore I got to do this. This is 1 over root 1 x on this guy, but this is equal to, this is 1, this is x, and then what is a dagger? It is x over square root 2h over m omega plus ip over root 2m omega h cross on 0. But that is the same as square root of 2h cross over m omega x on phi naught of x, because this is going to act on this and just produce a number, and the rest is phi naught of x, which we already found out there, and then plus what should be minus? A dagger is minus, that is right, good. A dagger is minus, and then I times minus I h cross. So minus h cross over root 2m omega h cross d over dx on phi naught of x. And we have phi naught of x, so all you got to do is to differentiate. That is guaranteed to give you the normalized eigenfunction. So please notice I am not normalizing each of these separately, I do not have to. I already constructed that 1 over square root of 1, whatever it is, took care of it automatically. So this is normalized, this eigenstate is normalized, this is a normalized eigenstate here. So it has got an added advantage that even the normalization of all these eigenstates is done in one shot. What kind of function would it be? Well, x phi naught of x, it has to be an odd function, we already saw it has got to be an odd function. This was a Gaussian, this is multiplied by x, and this is the derivative of a Gaussian, so it has again got an x outside. So it is of the form x e to the minus x squared. And what would its solution, what would it look like? So psi naught of x looks like that, phi 1 of x looks like that. Similarly for phi 2 and so on. Yeah, okay, we should terminate now, we should end this, okay, and so on. I leave you to find out what phi n of x is. It is a little painful to do this by differentiating and so on, but the nth one is going to be an nth order polynomial, and phi n of x is, apart from some normalization constant, it is the Hermite polynomial x in these dimensionless units times this Gaussian. Where this is the nth Hermite polynomial. H0 of x is 1, H1 of x is 2x, and so on. Next time I will mention a few properties of these polynomials. This is one of a family of orthogonal polynomials, and those are the solutions to the harmonic oscillator problem. We will also see why this is so significant, why these solutions are significant. They turn out to have very, very interesting connections. Their Fourier transforms, what would their Fourier transforms be? Well, this problem is sort of symmetric in x and p, so you would expect the position space and momentum space eigenfunctions to be exactly the same. So the Fourier transforms of these combinations are again Hermite polynomials times Gaussians in p. They look exactly the same in units of square root of 2m omega h cross. They look exactly the same as this. This also has implications for Fourier transforms itself, because it says that the harmonic oscillator eigenfunctions in a sense are the eigenfunctions of the Fourier transform operator in function space. So it has got close links with many other things, and we will point out some of them. Okay, let me stop here.